Hello, welcome to the playlist of videos on essential statistics for data science. I'm Hemukumar Kasala, and in this session, I focus on sampling distribution of sample proportion. Let's start with a problem to understand the relevance of this topic. According to a report, 7% of the cardiac patients who have undergone blood transfusions contracted viral hepatitis subsequently. Hence, a blood screening procedure was introduced in order to reduce the cases of viral hepatitis contraction. It was found that 6 out of 200 patients, that is 3%, were found infected with viral hepatitis after introducing blood screening. Since 3% is much less than 7%, can we with some confidence conclude that the blood screening procedure has succeeded? To answer this question, one needs to understand population proportion, sample proportion, sampling distribution of sample proportion, mean and standard deviation of sampling distribution, Z-curve, and probability measurements. It is important that one has gone through this previous video on sampling mean distribution and central limiting theorem in order to have an understanding on Z-curve and central limiting theorem. Let's get into the video. The objective in many of the statistical studies is to find the proportion of individuals or objects in a population that possess a particular property. For example, the proportion of customers who buy a refrigerator of certain brand also buy the extended warranty. Property in this case is possession of extended warranty, yes or no. Similarly, proportion of people who consume decaffeinated coffee among the coffee consumers in a community. Property in this case is consume decaffeinated coffee, yes or no. The proportion of individuals or objects in a population that possess the property under study is represented by pi. Pi equals individuals or objects that possess the property divided by the population size. Individuals or objects that possess the property are labeled as successes, S, and the rest of the population are labeled as failures, F. Hence, population proportion pi equals number of successes, S, divided by the population size. Population proportion pi ranges between 0 and 1. Pi multiplied by 100 equals percentage of successes in the population. Pi may not be known prior hand always, and hence inferences about pi will have to be made out of samples extracted out of that population under those circumstances. A sample of size n extracted out of the population under study shall contain a sample proportion p corresponding to the property of interest, where sample proportion p equals number of successes in the sample divided by the sample size n. Like pi, p lies in the range between 0 and 1. Sample proportion p is a random variable and its value varies each time a sample is drawn. Repeating the sampling and evaluating the sample proportion p over a long run results in a probability distribution for p, which is called as sampling distribution of the sample proportion. However, the characteristics of the sampling distribution of p, namely its mean mu p and standard deviation sigma p, are dictated by the population proportion pi and the sample size n. The above relationship between the sampling distribution of p, population proportion pi, and sample size n help make inferences about pi from the sampling proportion p. Let's look into some examples to understand the relationship between the sampling distribution of sample proportion p, population proportion pi, and the sample size n before arriving at the mathematical relationship between them. To a state university in summer in the current year, 16,636 students enrolled, out of which 6,983 students were female. If student being enrolled is female is considered as success and male as failure, then the population proportion in this case is pi equals 6,983 divided by 16,636, which equals 0.42, which is 42%. Let's do sampling to try and understand the sampling proportion distribution for different values of sample sizes n, 5, 10, 25 and 50. We choose 500 samples for each of the above value of n. For a sample size of n equals 5, the possible values of success S in each sample are 0, 1, 2, 3, 4 and 5. The corresponding values of the sample proportion P are 0, 1 by 5, 2 by 5, 3 by 5, 4 by 5 and 5 by 5, which equals 0, 0.2, 0.4, 0.6, 0.8 and 1.0. Plotting the histogram for relative frequencies, that is probabilities, for all possible values of P for 500 samples of size n equals 5, we have this. Let's take a closer look at this histogram and understand its characteristics. Histograms show higher relative frequency value for P at 0.4, which is close to the pi value 0.42. Non-zero relative frequencies for P values 0 and 1 are quite visible because, given the smaller size of the sample n equals 5, relative frequency, that is fraction of occurrences of all failures P equals 0 or all successes P equals 1 is sizable compared to the rest of the P values. In other words, it is easier to catch the successes or failures entirely when the sample size is small. Increasing the number of samples from 500 to infinity will result in the relative frequency values for each value of P converging towards its long-run actual probability values. The converging histogram fits into a positively skewed, slightly asymmetric probability distribution curve with mean value equal to pi at 0.42. Choosing a sample size of 10, the possible values of success in each sample includes all integer numbers in the range 0 and 10. The corresponding values of sample proportion P are 0, 0.1, 0.2, etc. up to 1.0. Plotting the histogram for relative frequencies for all possible values of P for 500 samples of size n equals 10, we have this. Higher relative frequency values for P still remains around 0.4, which is close to the pi value 0.42, even as n is increased. Non-zero relative frequency values for P values 0 and 1 are much lesser compared to the sample size n equals 5. This is because catching all successes or all failures in a given sample of size n equals 10 is relatively bit less possible when compared to the sample size n equals 5. The probability distribution curve that fits the histogram for n equals 10 is a bit less asymmetric compared to the one for n equals 5. In fact, the probability distribution curve tends towards a normal distribution with increasing n. However, mean value of the distribution remains the same value that equals pi, which is 0.42. The histograms for varying values of n, 5, 10, 25, 50 are shown together for comparison. The probability distribution curves that fits the histograms for varying values of n are shown superimposed. The histograms tend to get narrower as n increases. Smallest variance for n equals 50 and largest for n equals 5. The probability distribution curve is more normal for n equals 50 while asymmetric for n equals 5. However, the long run mean value as the number of samples tends towards infinity for all these distributions remain the same and equal to the population proportion pi, which is 0.42. As part of another study, it is recorded that 7% of the people who undergo multiple blood transfusions contract viral hepatitis. The population proportion pi in this case is hence 0.07. Histogram distribution for sample proportion p for different values of sample sizes n, that is 10, 25, 50 and 100, with 500 samples for each of the above value of n are shown. As discussed in the previous case, the probability distribution curves fitting the sample proportion histograms tend to get normal with increasing n. Variance reduces with increasing n, and long run mean values for all these distributions, that is when the number of samples tends towards infinity, remain the same and equals the population proportion pi at 0.07. Notice the superimposed sample proportion probability distribution curve for the viral hepatitis study case is more positively skewed, that is more asymmetric compared to the female candidates enrollment study case on the right. The reason is the value of the population proportion pi. If pi is much less than 0.5, then the probability distribution is more positively skewed. If pi is much greater than 0.5, then the probability distribution is negatively skewed, and if pi value is around 0.5, the probability distribution is less asymmetric. Having spent enough time on the details related to the relationship between sample proportion p, population proportion pi, sample size n, and the sample proportion probability distribution, we can take a look at the mathematical relationship between the sample proportion p and its probability distribution with the population proportion pi and given value of the sample size n. With p representing the sample proportion of success in a sample of size n extracted out of a population where the population proportion equals pi, the long run mean value for p represented by mu p equals population proportion of success pi for any value of sample size n. Hence, rule 1 in summary is mu p equals pi for any sample size with n taking any value between 1 and population size n. Rule 2. The standard deviation of the probability distribution for p represented by sigma p equals square root of pi multiplied by 1 minus pi divided by n. Thus, standard deviation sigma p for a given value of population proportion of success pi decreases with increasing sample size n and vice versa. Rule 3. When pi is neither very close to 0 nor 1 and n is large, the sampling distribution of p is approximately normal. Conservative rule of thumb is that the sampling distribution of p is approximately normal when n multiplied by pi is greater than or equal to 10 and n multiplied by 1 minus pi is greater than or equal to 10. In other words, n should be greater than or equal to 10 by pi and greater than or equal to 10 divided by 1 minus pi. 10 divided by pi is greater than or equal to 10 divided by 1 minus pi when pi is less than or equal to 0.5, and 10 divided by 1 minus pi is greater than or equal to 10 divided by pi when pi is greater than 0.5. Using this, the rule of thumb can be simplified as n should be greater than or equal to 10 divided by pi when pi value is less than or equal to 0.5, and n should be greater than 10 divided by 1 minus pi when pi value is greater than 0.5 in order for the probability distribution curve to be approximately normal. For example, when pi equals 0.4, then n should be greater than or equal to 10 divided by 0.4, which is n should be greater than or equal to 25. Similarly, when pi equals 0.7, then n should be greater than or equal to 10 divided by 1 minus 0.7, which results in n greater than or equal to 34. From the above discussions, one can deduce required sample size n to achieve a normal sample proportion distribution is relatively smaller when the population proportion pi is close to 0.5 and much higher when population proportion pi is away from 0.5. Let's apply the understanding we had so far on sampling proportion distribution using the problem that I posted in the beginning of this video. According to a report, 7% of the cardiac patients who have undergone blood transfusions contracted viral hepatitis subsequently. The population proportion pi in this case is 0.07. Hence, a blood screening procedure was introduced in order to reduce the cases of viral hepatitis contraction. Post-introduction of the blood screening procedure, a sample of 200 patients who have undergone blood transfusions were chosen and were tested for viral hepatitis. It was found that 6 out of 200 patients were found infected with viral hepatitis. That is, the sample proportion P in this case equals 6 divided by 200, which is 0.03, in other words 3%. Since the sample proportion P equals 0.03, which is 3%, is quite less compared to the population proportion pi, which is 0.07, can we conclude that the blood screening procedure has succeeded and hence this lower sample proportion value? Or should this value 0.03 be attributed to the possible variance in the sample proportion distribution, and hence this reduction cannot be attributed to the introduction of blood screening? Let's conclude this analytically based on the sample proportion understanding we developed so far. Since pi is much less than 0.5, n should be greater than or equal to 10 divided by pi for the sample proportion distribution to be approximately normal. 10 divided by pi equals 10 divided by 0.07, which equals 142.9. Since n equals 200, which is greater than 142.9, the sample proportion distribution can be safely assumed to be normal. We can proceed to calculate the z-score. Z equals x bar minus mu p divided by sigma p. Please refer video on sampling mean distribution and central limiting theorem for z-score and central limiting theorem understandings. Z equals x bar minus mu p divided by sigma p, where x bar equals the sample proportion p measured, which is 0.03. Mu p equals the sample proportion distribution mean, which is nothing but the population proportion pi, which equals 0.07. And sigma p equals the standard deviation of the sample proportion distribution. Sigma p is given as square root of pi multiplied by 1 minus pi divided by n. Substituting the values we have, square root of 0.07 multiplied by 1 minus 0.07 divided by 200 equals 0.018. Substituting the values for x bar, mu p and sigma p, we have z equals 0.03 minus 0.07 divided by 0.018 equals minus 2.22, as the value for z-score. Hence, the probability of getting a sample proportion value p less than 0.03 equals probability of z value less than minus 2.22, and from the z table that can be derived as 0.0132, which implies the probability is 1.32%. In other words, the probability of getting a sample proportion value p of value 0.03 is as low as 1.32%. Since the probability of getting a p-value which is as low as 0.03 equals 0.0132, in other words 1.32%, is very low, it suggests that p-value 0.03 is far enough from pi value 0.07, and it is very rare to get such value just due to the variance of p around pi. And hence the conclusion is the blood screening has indeed reduced the contraction of viral hepatitis post blood transfusions. That brings us to the end of the session on sampling distribution of sample proportion. Please leave your comments, questions if any, and I'll try and revert back as soon as I can. Thank you for watching. See you with the next session. Until then, bye.